Okay, with all the terms that we've learned in the videos up to this point, we're finally ready to start talking about organic reactions, aside from acid-base reactions. Today we're going to introduce the SN2 reaction, which is one of the simplest organic reactions. We'll talk about drawing arrows for any substitution reaction, then we'll talk about the SN2 reaction in particular, its kinetics, stereochemistry, and things, substrates or starting materials that readily undergo SN2 reactions. Okay, so before we talk about reactions, we need to talk about the structure of alkyl halides. There's three types of alkyl halides you can have. Primary, which means that the carbon that's bonded to the leaving group or to the halide is bonded to one carbon, two carbons, or three carbons. These are called primary, secondary, and tertiary, much like carbocations that we introduced previously. It can be primary, secondary, or tertiary. Okay, so if in any substitution reaction there's two possibilities. You can have a concerted mechanism, meaning that everything happens in one step. In this mechanism, right, we have the nucleophile is attacking, so we have a nucleophilic attack step and a leaving group step, but it's all happening in the same. So we have a nucleophilic attack arrow and a leaving group arrow, but it's all one single step. They're happening together in a concerted fashion, meaning everything happens at the same time. So the nucleophilic attack, the nucleophile attacks, and the leaving group leaves together. That's one step. This can be contrasted with a stepwise mechanism where the leaving group can leave first. That's an acceptable mechanism, right? That's one step that gives us an intermediate carbocation, which can then undergo a nucleophilic attack. So this would be a two-step mechanism, otherwise known as a stepwise mechanism. So what if we switched the order of the steps, right? The problem with that is you can't have a nucleophile attack to give an intermediate, which then the leaving group leaves from, because carbon cannot make 5 bonds. This is not a reasonable proposal. Okay, with that in mind, let's talk about the SN2 reaction. The SN2 reaction is an example of the first kind. It's a concerted reaction where the nucleophile attacks at the same time that the leaving group leaves. Okay, so as we mentioned before, this is one step. There's a single step here, two arrows, one bond is forming and one bond is breaking. So these two things bump into each other in solution and react. So because of that, there's a very easy way to write a rate equation for this reaction. The rate of this reaction is going to be equal to some rate constant K times the concentration of the nucleophile times the concentration of the electrophile. So the nucleophile is raised to the first power, the electrophile is raised to the first power. So this is called a bimolecular rate. So SN2 stands for Substitution Nucleophilic Bimolecular. Another way to think about this is a bimolecular rate means two things have to bump into each other in a single step, right? So we have two things bumping into each other. What is important to recognize about a bimolecular rate, and this makes sense, right, is if we decrease the concentration of one of our reactants, the likelihood of those two things bumping into each other is going to decrease, so the rate's going to decrease. So that's why the rate depends on both the concentration of the nucleophile and the concentration of the electrophile. If we change one or the other, if we increase the concentration, that will increase the rate of either the nucleophile or the electrophile. If we decrease the concentration of either one, that's going to decrease the rate. Okay, so let's talk about good nucleophiles and leaving groups for the SN2 reaction. To start with, we have these halogens, which we've already talked about. Iodide, bromide, and chloride are good leaving groups in an SN2 reaction. Fluoride is not a good leaving group because it's not the conjugate base of a strong acid. These are very, very weak bases because they're resonance stabilized. So triflate, mesylate, and tosylate are also good leaving groups. And what we'll see later on is that water and alcohols can also be good leaving groups. What are some good nucleophiles? Well, we have some very good nucleophiles, and iodide, bromide, and chloride are good because they're polarizable. And we'll talk about this later. And most things with a negative charge will be good nucleophiles, and then sulfur-containing nucleophiles are also good nucleophiles because they're polarizable. Water and alcohols can also be weak nucleophiles. Fluoride is a weak nucleophile. So these are the kinds of nucleophiles and leaving groups that we'll see in substitution reactions. So we're going to substitute one of these bonds to a leaving group for one of these bonds to a nucleophile, as we'll see. So how does the SN2 reaction work? Well, remember, this carbon has a partial positive charge, and this chlorine has a partial negative charge. So the nucleophile comes in and attacks, but it does so by backside displacement. So hydroxide attacks the carbon, which starts to push the hydrogens into a planar arrangement, and then you want to think about this thing flipping inside out like an umbrella in a really windy day. The hydrogens get pushed forward, and at the same time they break the bond to the chlorine. This picture right here would be our transition state. Remember, since this is a single step, the potential energy diagram would look like this. It would be a one-step mechanism. This transition state would be the very tippy top of the peak here. The reactants would be right here, the products right here. If this is a spontaneous reaction, then products should be more stable or lower in energy than the reactants. This is called backside displacement. So in the transition state, this bond is partially formed and this bond is partially broken. Okay. So why do these reactions occur by backside attack? Well, it has to do with molecular orbital theory. So in the previous example, right, we had chloromethane undergoing attack by hydroxide, right? So if we look at the bonds or the orbitals that are involved in methyl chloride, what we have is carbon is sp3 hybridized, right? And I'm just going to draw that bond. So we have an sp3 hybrid orbital on carbon that's overlapping with the sp hybridized orbital on chlorine, right? And we have 2 electrons in this orbital, right? But anytime you combine 2 orbitals, you create 2 new orbitals. This is our sigma bond. But we also created a sigma star, which is higher in energy, which looks kind of like this. You have a node between carbon and chlorine. You have an anti-bonding orbital on this side, and you have an anti-bonding orbital on this side. This is empty. This is an empty sigma anti-bonding orbital, which is illustrated by this lobe in the picture. So because it's an empty orbital, it can accept electrons from a nucleophile, right? But notice that it's on the opposite side of the carbon as the bond to the chlorine. So if the nucleophile comes and dumps electrons into this empty orbital, it's doing it on the complete opposite side of the carbon-chlorine bond. I'm a nucleophile, and I'm coming in and attacking on the opposite side of this carbon-bromine bond in this particular case. Okay, so why do we care about which side of the carbon is getting attacked by the nucleophile? Well, it has implications in terms of stereochemistry, right? So if we start with this electrophile, it's in the S configuration. The nucleophile comes in and attacks, which flattens it out in the transition state and pushes the groups over to the other side. And notice now that we've changed the stereochemistry from S to R. This is a common feature of SN2 reactions, which we're going to call inversion. So one thing that we often say is that SN2 reactions proceed with inversion of stereochemistry. So if you start with the S configuration, you'll get R, and if you start with the R configuration, you'll get S, because of the backside attack that's taking place. Okay, let's talk about the rate of SN2 reactions for different alkyl halides. As we'll see, methyl halides, like in this case methyl bromide, undergo really fast reaction, 1,000 times faster than a secondary. Primary undergoes reaction, SN2 reaction about 100 times faster than secondary. Secondary is pretty slow compared to primary and methyl. Tertiary does not go. Okay, so what we can say is that increasing the substitution, so if we have a tertiary alkyl halide, it's going to not really undergo SN2 reaction at all. SN2 is slow. Secondary is slow. Primary is fast. Methyl is very fast. And we'll say tertiary is no-go. So we're never going to see a tertiary SN2 reaction. Why is that? So why would, and substitution is also called sterics. So the more sterics that we have around this carbon, the slower that it undergoes reaction. Why would that be? Well, if we go to the previous slide, right, remember my nucleophile is trying to come in and attack this carbon. As we increase the size of these groups, the nucleophile, as it comes in, is going to be encountering those big groups that are surrounding the carbon and blocking its entry. That's called steric bulk. What we can do to rationalize this is that imagine as the nucleophile is approaching, if it's getting repelled by those really big groups, that's going to lead to a higher energy interaction. So what we can say is that as we increase the bulk surrounding that carbon, that increases the energy associated with the transition state because we're trying to jam in something into a very crowded space. That's a high energy interaction. As we increase the energy of the transition state, that also increases the activation energy, which means that reaction goes slower, right? So as we increase substitution, we increase the energy associated with the transition state, which means we decrease the rate. The rate goes slower because we've increased the energy associated with the transition state that leads to the products in those cases. So as I mentioned, increasing substitution increases the energy of the transition state, which decreases the rate. The rate is slower as we increase the energy associated with the transition state. Okay, so we've talked about one-step mechanisms for SN2 reactions. Are there such things as SN2 reactions that have several steps? We can have a proton transfer at the beginning, which is fast, or a proton transfer at the end, that's fast, but the rate determining step for an SN2 reaction is always going to be this concerted nucleophilic attack followed by loss of a leaving group. But let's look at some examples of these. So hydroxide is not one of the okay leaving groups. You can't have hydroxide as a leaving group, but this compound can undergo substitution in the presence of sodium chloride and sulfuric acid. So how does this work? Well, what's happening is initially we have a proton transfer step. So sulfuric acid is an acid. This acts like a base. We protonate the oxygen, and now we turn it into a much better leaving group. Now chloride ion can attack at the same time that the leaving group leaves to give chloromethane. So in this particular case, the proton transfer happens first, followed by a concerted nucleophilic attack and loss of a leaving group. Okay, so there's two possible mechanisms for substitution. What we talked about in this video is the SN2 reaction. The SN2 reaction, as I mentioned, stands for Substitution Nucleophilic Bimolecular. So the rate depends on the concentration of both the nucleophile and the electrophile. I want you to know how that affects kinetics. So if you decrease the rate of one, either the nucleophile or the electrophile, or both, that decreases the rate. If you increase the concentration, that will increase the rate. Know that the stereochemistry proceeds by backside attack, which results in an inversion of configuration. Be able to predict the stereochemistry of any SN2 reaction. Know how to draw potential energy diagrams for an SN2 reaction. It's going to be a single step in the transition, and know how to draw a picture of the transition state, and also know that increasing the substitution of the halide decreases the rate of the SN2 reaction, with methyl being the fastest, followed by primary, followed by secondary, which is much faster than tertiary. This pretty much does not undergo SN2 reaction.